So this is, remember, the power supply. I changed this transistor on the power supply because this one is exactly the same type as the rest of the transistors in my power drive, and I just wanted all 5 of those to be the correct type. So here it's really not that critical. It's just I just put in one that can do a lot more high voltage for this one, so it's perfectly fine. And I tested this one is now working fine, and now I got my spare transistor. So I have, of course, repaired this. So now I got all 5 of them, BDY 56. And that one will be the new one. Oh, new old one. And I changed the resistors because they were looking a little bit nasty. And I've been thinking a little bit about this circuit. How is it really done, and what is the purpose of everything here? So I came up with this little summary of what I've figured out. So this is the top 2 converters, and it's mounted like this, and this is the main output. So now the fun thing, I didn't know that before now, so this is new knowledge. So look at this positive and negative. This goes via this and then to the output right here, okay? But since this is plus, or this is the 2 kilovolt output, it is actually +1 -1. So here is the center point to the ground point, and this is also chassis, DC input ground, and all that kind of stuff. So there's a series resistor, and this one is connected to the center point of those 2 converters. And those 2 converters, they of course make positive 500 and negative 500 from this center point. And the plus and the minus 500 goes to this system here, and it becomes plus 1000 and negative 1000, and that is how it's working. All right, so now the fun thing, this is also why they're using all those resistors. Everything is balanced, so they, funny enough, they divide the output voltage with half of those, and this becomes the voltmeter, and the other half of those resistors become the, again, a balanced measurement, a positive and a negative voltage input to the opamps here. And that means that is why they are using that crazy amount of opamps for everything, because everything is completely balanced, positive and negative. So that is a little bit funny. They're doing the same with the current measurements. And here we got the current measurement resistors, and that will be the current sense for the amp meter. And again, all those resistors, they go into the current system, and that is why it wasn't working when I just input something here. It needs to be correctly balanced, and that is definitely why I think it is not working. So hopefully all this will get up and running maybe tomorrow. I think I spent like a whole week on this thing already, but I got even more. I will take the camera here and show a little detail. I keep finding all sorts of defects. Look at that, the orange wire out of this transformer. This is of course not good. So one of the windings is open, and that means all the reverse voltage here goes absolutely berserk because there is no reverse diodes. And here what happens is you're going to have all sorts of flash over and all sorts of problems. So I will of course repair this, but then why don't I? Probably easier to show on one of the others right here. So that'll be the windings, the 2 secondary windings, the 2 high voltage windings on each of the transformers. All right. So there's a diode, and this generates a positive. Okay, so here's another diode. This generates a positive. And they are, of course, in series. So what I could have done is put a diode over this one, and over that one. So if anything fails here, all my nasty high voltage from the previous stage will just go straight through to the output and not cause any extra damage. And that is what I want to do on all 4 sections. So here is a very fast and super quick drawn schematic of this rectifier system I just explained about. So it's probably a little bit easier to see how it is on a schematic. So let's pretend we don't have a connection with this red mark. And now you can definitely see what's going to happen if we have 3 or more of those systems in series. All voltage will now go over this bottom capacitor, and it's probably going to blow up and cause all sorts of problems. But if I put in the green marked diodes like this, then we can now handle any sorts of problems with one of the 4 high voltage systems. It can also be on the primary side, the transistors, the drivers, whatever problem, it will just continue to work and not just blow up. I also realized I forgot to explain exactly how this driver system works to the output stage. We have already seen the output stage right there. Okay, so this is the pre-driver and the output driver for the final stage. And we got some inductors and some different transistors, and I actually made a complete schematic of this entire part. And you can let's take it from the back. We got 4 parallel NPN transistors, and they are driving all 4 primary windings on all the high voltage transformers. So of course this is just a classic pre-driver, and it's a Darlington sort of system, right? And then we got this PNP transistor, and this one is turned on by pulling this one low. So you pull the base low, and then you activate this PNP transistor. And then look at that tiny little NPN transistor right here. This one is very, very interesting. At the beginning, I had the idea, how is this ever going to turn this one on? That is not what it's doing. I'll show in a second what it's doing. So, my oscillator signal comes here. It's AC coupled. It goes to my first little inverter driver. So there's just a high voltage here. And then my pulses just goes straight here. Pulse, pulse, pulse. And then you'll see the signal here pulls down, and there's a resistor right here. So this is a current generator, and this pulls the base active this way. So this current that flows this way actually energizes this inductor. And here is the fun thing. When you want to turn this off, see what happens? Now the current goes lower and lower and lower, and this one is now fully off. Now the energy stored in this inductor is now released to a positive here, and this positive now activates this NPN transistor, and now this shorts this transistor to kick it off as fast as possible. And this way we minimize switching losses in all this by turning it off really, really fast. So that is very, very fascinating drive and switch off circuit, and that is why it was important to try and show all this and how they have done it. And this is this PNP transistor here is connected to different op-amps driving those 2 sides here, so to turn it on and off. And it's also sensing the signal and synchronizing to the PWM and then making it shorter. And here is my little schematic of this connector that goes here to the main side. We have the B side and the A side, and it's 2 times 15. So that is why this top here is B. And that will be the green connector inside the cabinet. Where is everything going and all that. And I think this makes a lot of sense in case you are debugging what is going on. This is the current range and watt range switch. And we got the different diodes. Some of the diodes, they have a common orange wire, and the high volt LED is not connected to this system. It's connected to something else. And that is my voltage potentiometer that was open, and that was why I figured this out. That was because now, since everything else was already okay and it was still not working, it had to be something related to all those input signals controlling whatever is what is going on here. I needed to figure this out. And this is my interlock, and this needs to be closed, otherwise it's just turning everything off. And yeah, so now we can continue with the power up of this unit. So here's another little funny part of the circuit. The 4 diodes and the transistor and the resistor we see here in the middle, all those 4 diodes, they are all connected, as you can see, to the top of all transformers. Okay, all 4 transformers got 4 tops, and they all go into the same point. And I made a little schematic because, of course, I wanted to know how is this working, how it's supposed to work, and then I could check all my components in this circuit and verify that it's all working. So what we have here is just one of the 4 transformers. We got one of the 4 power transistors, and this is just this one common driver. That will be the 4 diodes that goes into this common point. We got a 27 ohm resistor, and then we got this PNP transistor that goes to ground. And this transistor is then activated via this NPN transistor. So you activate this one, and then it pulls down the base. This way, activate this one. So there's an active clamp circuit for the flyback converter. So it activates this inductor, charges the inductor, and when it releases the power, then it flies back, and then it clamp the signal so it's not flying way too high, but it's clamping it down to ground. And this is a little bit special. I would have made it so it clamps it to 46 volts and not to ground, but this way the current can flow around and not just being killed to ground. So it's a little bit weird the way that they made this circuit, I must say. It's everything here is just weird and special. But anyway, both of my transistors, they work, and I put them back in, resoldered everything, cleaned it up real nice and fine, and that will be my diodes that I put over all capacitors. So if and when one of the power drivers or one of the transformers or one of the solderings, one of the rectifier diodes, whatever goes wrong, we're not going to have any bad side effects. So we have the diodes on each of the 4 systems. So I really hope this is going to be one of the final times that I reassemble this. I tried my very, very best to make it look as nice and beautiful as I possibly can. And here is the connector, like that. And then I should just try and plug it in. Now the loop is closed. We got all the high voltage converters running. And the only thing I really would like to see is the AC signal that drives the PWM. Maybe I can sneak this out from the driver board and get my scope to monitor this one at the same time. I think that's a good idea. As a little celebration, look what she made me. Ooh, popcorn to celebrate. Nice. So this is my first power up in a closed loop mode actually. And this is the dangerous kind of thing. My voltmeter is completely down, so it shouldn't do anything at all. So let's try and power it up. And that is a good sign. We got 0 volts, we got 0 PWM, and then I should actually be able to give it a little bit. What we see here is a little bit of PWM. And we already see the high voltage. So that means I know that we have more than 10 volts on the output, and I should be able to turn it down and it shuts off. So far, so good. So now I've connected high voltage probe and my little cool remote voltmeter. Let's try and power it up again, and let's do exactly the same test. So 100 millivolts, that means 100 volt. So this is the first 100 volt. We can now see here the PWM. This is the tiny little pulses, and it's using about 10 watts. All this is perfectly fine. So let's see if we dare to give it more. So this is 500 on the meter here. So it's very, very close to 500 in reality. And this is, we got 10 volts per division. And this is, by the way, no, this is the driver. This is the driver transistor, and we got 10 volts per division. Ooh, we got some trigger issue. Like that. 1000. And it's using 18 watts. What I really would love to see is the current regulation works. If I crank this all the way down, I would expect it to shut down as well. So let's see what happens. No, there is also no load. So probably this is not working. So I should be able to try and load it and see all that is working. So far it's not going to 0, but it says here actually 2 milliamps as the minimum. So we need to have at least that before this one should work. So this is what I should expect. Okay, fine. So let's at least just try the 2 kilovolts of output and see if that is working before we call this a success. $1,500, and let's see what we can. Oh, that was only my current limit on my power supply. So let's do it again. We should be able to make the 2000. Here we go! 2000! Yay! And it's using 28 watts in idle. That is a lot. really would like to see this current. Doesn't matter. Let's just give it 400 volts. The voltage isn't really important here. So this is our current limiter. Let's put it all the way down to only 2. Let's try and play with the load. Oh, look at that. It goes to current limit. But it's in pulse, it's pulsing. That is weird. That is the weirdest of the weirdest. So this is how this, see? Pulsy, pulsy, pulsy. Blinkety, blinkety, blinkety. But it kind of works. Well, that was 5 milliamps, but yeah. It kind of works, but that is of course maybe the timing and the loop time in the current regulation and my load here and this load loop regulation is fighting each other, and this is probably why we have this oscillation. If I take a resistor, it's probably not that bad. So okay, in times 1, this amp meter should be 20 milliamps. So why can't I see the 5 milliamps? Okay, so let's give it 4. So 4 should be right there, but I don't really see anything, do I? I don't see a response. Oops, that was embarrassing. Okay, let's just erase the last bit of the video and let's pretend that didn't happen. You can of course imagine I forgot to plug in the current meter connector. Oh, that was dumb. Anyway, here we go. Look at the amp meter. And then I can just crank up my load a little bit, and that means I should be able to, yeah, look at that. And then we can have a lot of milliamps. I really love it. It seems to be working. So we've got current regulation, and we can turn this off and go back to voltage regulation. Don't you think it's really nice to have a load that can handle, I mean, a lot of voltage? This one can only do 1000 volt. And well, I don't have a DC load that will handle more than 1000. So maybe it's time to build a new one. All right, but I think this unit works so far. So I really don't want to make this video any longer. So thank you so much for for watching. If you have been here this long. Wow, that is the coolest, craziest DC power supply so far. And the next thing I want to do is I want to change this big hefty transformer that is just way too big and way too heavy, and I'll just put in a little 48 volt switch mode converter because they cost almost nothing, and I mean, this is really what we want, right? Instead of this, so it can be smaller and more lightweight, more convenient to work with. Now it's up and running. Okay, bye bye, see you.